Hello and welcome again to today's video. In this video we're going to be concerned with the classification of local extreme points. As you might remember, we already did things like that. We used stationary points to find candidates for extreme points of differentiable functions. And then we looked at the monotonicity of a function to find out whether a stationary point was a local extremum and whether it was a minimum or a maximum. In this video here, we're going to find a different criterion for classifying local extreme points that involves higher order derivatives, in particular the second order derivative, but we might also have to resort to even higher orders. Now this section is called classifying local extreme points. The idea of that is pretty simple. Remember, for monotonicity, we had a look at the function f prime. And now a point was an extremum if f prime was either positive before and negative after, so it increases and then decreases, or if it was negative before and then positive after, it decreases and then increases, so we'd have either a maximum or a minimum. And what that means is, of course, the slope of f prime will change, and the slope of f prime is given by the derivative of f prime, so that is f double prime. That means we can just have a look at f double prime to see if f prime has a change in slope. So basically, again, if we have a function f that first increases and then decreases, then we have a local maximum here, so that is f quantitatively. Then what about f prime? Well, for f prime, we would then know that it has to change its sign. So it's first positive and then negative. So the sign of f prime changes. First positive and then negative. That of course means f prime has to be decreasing. And that in turn means f double prime has to be negative if f prime is decreasing. And of course the same is true for the situation where f has a local minimum. Now in this case f will first be decreasing and then increasing. And what that means for f prime is it's first negative and then it's going to be positive. So that's f prime. Again, there's a sign change. Now from negative to positive, f prime is increasing. And that in turn would mean we'll need f double prime to be positive to be sure that f prime is increasing. And we could infer from that then that we have a local minimum. So basically that is the contents of the following theorem. And that theorem is called a second order condition because it involves the second order derivative or even higher derivatives. One can generalize this a little in case the second order derivative is 0. There might still be higher order derivatives that will give us the necessary information. I'll give you the details in just a second in this theorem. So second order condition. For local extrema. And the precise statement here is the following. Let I again be an open interval. And let f be a function defined on I to R. And let's say there is a k. So if there is a k, a natural number not equal to 1, but higher than 1, such that the following is true. What we want is f is k times differentiable in I. What we also want is, for a stationary point, x star, the following holds. So what we have is the first order derivative of x star is of course 0 because it's a stationary point. And so are all other derivatives up to order k minus 1. And then the kth order derivative here, fk of x star, is not 0. So usually k will be 2, and then you can just say, well, the first order derivative is 0, and the second order derivative is not. And if this is satisfied, then the following holds. Part 1. And that, again, that is the usual part here, or part of that usual part, if k is even. So for example, 2. And then we can look at the sign of that kth order derivative, fk of x star is, let's say that's negative. Then x star is a local maximizer. Remember what we've seen here? If f double prime here is negative, then that would mean f prime is decreasing. And if it crosses the 0 here, then that means f is first increasing and then decreasing, so we have a local maximum. Okay, that is this case here. So if k is even with negative kth order derivative, then x star is a local maximizer of f. Part 2, if k is even and the kth order derivative is positive, then we'll have a local minimizer. So if k is even and the kth order derivative at x star is positive, then x star is a local minimizer of f. And finally, point 3, that says if k is odd, then x star will not be a local extreme point. So if the second order derivative is still equal to 0, but the third order derivative is not, then we can be sure that x star is not an extreme point. If the third order derivative is still 0, but the fourth order derivative is not, then we can again use these here, and we're again back in the case k is even. And that's a generalization here. So we look at the even order derivatives to find out if we have local maximizers or minimizers, if all the ones before that were 0, and if we have all the ones before that 0, and then an odd order derivative being the first non-zero derivative, we can be sure that's not an extreme point. Again, let's look at an example here. And we just revisit an example that we had earlier, but I'll quickly go through the motions once again. So let's say f of x equals 2x to the power of 3 minus 9x squared plus 6x plus 20. Then f prime of x was 6x squared minus 18x plus 6, or 6 times x squared minus 3x plus 1. And let's also compute f double prime, and f double prime is 12x minus 18. Or you could express that as 6 times 2x minus 3. And just for the sake of completeness, let's also compute f triple prime. That is simply 12. So f triple prime is sure to be non-zero, but hopefully f double prime already is, and then we can make we can find out whether we have local extrema that are minima or maxima. As usual, we first have to go for the stationary points. Now, f prime of x is 0 if and only if x squared minus 3x plus 1 is 0. And that's the case if and only if we just use the formula for quadratic equations to solve for this. x1, x2 is 3 plus minus the square root of 9 minus 4 over 2. So we get two stationary points. x1 is 3 minus the square root of 5 over 2. And x2 is 3 plus the square root of 5 over 2. I'm going to find out whether these are local extrema, and if so, of which type. So we'll use the second order derivative for the classification. f2 prime of x1. Remember, f2 prime is 12x minus 18, or 6 times 2x minus 3. So what we get for x1 here is 6 times 3 minus the square root of 5 minus 3. So that is 6 times minus the square root of 5. And that surely is negative. So that means we have a local maximum here. Right, f2 prime is not 0. The order is even, and that means we have a local maximum. And the second one, f double prime of x2, is again 6 times 2x2 minus 3, or 6 times, well, x2 was 3 plus the square root of 5. So what we get here is 3 plus square root of 5 minus 3. So there's 6 square root of 5. And that surely is positive. So again, non-zero and positive. And that means we have a local minimum here. Okay, so in this case, we can classify those into local minima and local maxima. Let's quickly have a look at one more example. Just a very brief one. Let's say we have a function g of x. We modify that example slightly. Let's say that's x to the power of 3 minus 3x squared plus 3x plus 10. And then we get g prime of x is 3x squared minus 6x plus 3, or 3x squared minus 2x plus 1, or 3x minus 1 squared. So the only stationary point here is 1. And let's also compute g double prime. G double prime is then 6x minus 6, or 6x minus 1. And g triple prime is 6. So that's non-zero. And the only stationary point is 1. We already said that. Stationary point, x1 equals 1. And we also have g2 prime of x1 equals 6 times 1 minus 1. So that is 0. but of course g triple prime of x1 is non-zero. So in this case, the first two derivatives are both 0 and the third one is not. So we have an odd k in this case. So we're in this case odd k. And that means x1 is not an extreme point. It is a stationary point, but it's not an extreme point here. And that concludes this second order condition video and the accompanying examples. In the following videos, we'll have a look into more applications of the derivative, especially with regards of approximating functions, because as you remember, we started with the motivation of approximating functions for the differentiation, and we'd like to investigate that a little further, and that will be one of the points that we'll take up in the following videos. I'll see you then.